We know that we use chemical formulas to represent compounds. Well, chemical formulas actually can either be molecular formulas or they can be a reduced form of a molecular formula called an empirical formula. So I like to say molecular formulas are like the exact deal. They are, if you have a molecule, they are the specific number of atoms of each type of element you will have in that repeating unit of a molecule. An empirical formula then sometimes is a reduced version of the molecular formula, and it just shows relative numbers of atoms of each type of element. So they just give the lowest whole number ratio of all of the elements involved. It's easier to show you the difference now. Let's see what you think. So, for instance, if we look at butane, this is the real deal of what a butane molecule has. It has 4 carbons and 10 hydrogens. If we were just to say that it has carbon and hydrogen, and we just wanted to give, excuse me, the relative numbers, we could divide by 2, and of course 4 divided by 2 is 2, and 10 divided by 2 is 5. So these both say the same relative number of carbons and hydrogens. So this is the reduced or empirical formula of butane. All right, what about water? Well, you can't take the number 2 and the number 1 and divide by a whole number other than 1 and get another set of whole numbers. So as it turns out, the molecular formula is equal to the empirical formula. There's no reduction that can occur. Let's see what you think about hydrogen peroxide. Call this the Santa Claus molecule, empirical formula, I guess. So notice that we can divide by 2 for each of these and get 1 for each. So H2O2 and HO is giving the same relative number of atoms of hydrogen and oxygen, but I will tell you this is the real deal and this is a reduced form. All right, hydrazine. Can you see how that works? Now be careful if you have to do these on a test because it's very easy to make a mistake. If I divide each of these by 2, this goes to 1 and this goes to 2. Okay, so that was 1 and that is 2. All right, let's see what else we got. A couple more. These are my favorite. So acetylene is C2H2. Of course, we divide the 2 and 2 by 1 and get CH. And a very, I think, different compound is benzene. So benzene has 6 carbons and 6 hydrogens. But notice that if we go ahead and write the empirical formula of benzene, it's just a 1 carbon to 1 hydrogen ratio. 1 carbon to 1 hydrogen ratio. So these both have the same, good example of having the same empirical formula, but the real deal molecules are very different. Yeah, I think that's cool. So recently I did a part on percent elemental composition, and the percent, when you get your answer for the weight percent that's brought by each element, that is relative by mass, whereas an empirical formula is relative by the moles of the different atoms. Okay, so weight percent, okay, and empirical formula give similar information, relative amounts, but one is on a mass basis and one is on a moles basis. So a minute ago when we looked at acetylene and benzene, remember they had the same empirical formula, C1H1. Well, actually, if we were to go through the process of coming up with the weight percent for both of those, they would have the same weight percent of carbon and hydrogen in each of those compounds. So there are a few, especially I guess ionic compounds, where if you were to, how do I say this? Oh, most ionic compounds are already written in the reduced form. Remember in lab, for instance, let's see if I can come up with an example. when you combine barium with oxygen, okay, and you crisscrossed and you got BaO, oops, sorry, well, you crisscrossed and you got Ba2O2, and I tried to come along and try to say, actually, we write ionic compounds like that is the reduced form, so BaO. Well, there are a few exceptions, so, and they hope they kind of make sense to you. Remember, one of my least favorite polyatomic ions is the mercury 1 polyatomic ion, and it looks like this, Hg2, 2 plus. Okay, that is, how do I say, you can't monkey with that unit. So when it combines with the chloride ion, the neutral formula would be written this way. If you were going to take that formula and go ahead and reduce it, actually its empirical formula would be H, you divide these by 2. Okay, so that's an example. Another example would be one involving ammonium. This is just an example. Now in this case, of course, ammonium is the NH4 plus, so you don't monkey with it. And here we're combining with nitrite, NO2 minus. We crisscross, and of course we get one of each, and that's kind of indicated here. Now that's how we would write ammonium nitrate, if we were going to go ahead and reduce it. Notice that actually we have 2 nitrogens, even though one is an ammonium and one is a nitrite. You divide that 2 by 2, you divide the 4 for the hydrogen by 2, and you divide the oxygen by 2, and you end up with this empirical formula. So we don't do that. So that's an example of ionic compounds where we write them as they really are, and we don't reduce them. Otherwise, we reduce them if possible. So that's actually just a side note. I spent quite a bit of time on that little side note. So these are problems then associated with this topic.